Hello, and welcome to Math321. Today I'm going to talk about minimum error. Specifically, I'm thinking about interpolating polynomials. Excuse me. Oops. Interpolation. This is going to really end up being a conversation about Chebyshev polynomials. But for the moment, we're just talking about interpolation. So the pointwise error interpolation function for an interpolating polynomial where xi of x lies inside some appropriate interval, and an omega n x is the product of monomials that look like this form. So to minimize the pointwise error, we don't get any control over the derivative, and we don't have any control over this point. That's a factorial, which we don't have any control over except for changing the degree of our interpolating polynomial, which, as we know, is not always appropriate. So the only thing we have control over is this. So if we want to minimize pointwise error, we need to minimize the size of this, and that's what Chebyshev polynomials do. Right. So I'm going to talk about the deviation. Let f be a continuous function over some interval into the real numbers, and I'm going to have Pn of x, a polynomial. So it's going to be something that looks a little bit like this. Then the deviation of f from the polynomial is going to be our maximum norm over all of our points. So this is the maximum of the absolute value of f of x minus Pn of x for x inside the interval that we're considering. I don't, there's caveats on that, of course. So there's a nice little theorem about these. So for all n, there exists a polynomial of degree at most n that minimizes the deviation over all polynomials. So the proof is rather long-winded and isn't particularly informative based upon what you've seen already. So if you do want to have a look at the proof, then go check out theorem 5.01 or 5.4.1 in Isaacson and Keller. Right, now with that definition we can define dn of f. So this is the minimum of the minimum of df(pn) over all degree n polynomials. Over all degree at most n polynomials. So sometimes you'll see this written as the minimum of d a0, a1 up to an. And that's because degree n polynomials have n plus 1 coefficients, and this is saying we want to minimize the deviation of a polynomial with these coefficients from f. nice little theorem. This is by de la Poussin, maybe. I'm not sure how to pronounce it. Anyway, this is an important theorem because it tells us something about how we find information about deviations. So let Pnx have deviation fxj minus Pnxj equal to minus 1 j ej, j equals 0, 1 to n plus 1, where a is less than or equal to x naught, and f is continuous inside our interval, of course, just as we've had all along. So in particular, if you can prove that these ej's are the maximum deviation, then you know that this polynomial must achieve the bound. The proof for this involves manipulation of polynomials and is therefore a little interesting, particularly for our purposes. Ooh, check that out. Flicker, huh? I don't think that's very good. I guess you're just going to have to cope with some shadows. Apologies. So the proof. So it comes in several steps. You know, there's n plus 2 of these. Assume that Qnx degree n polynomial is such that dfqn is strictly less than the minimum of this ej. Okay. Then Qnx minus Pnx, which happens to equal fx minus Pnx. This is by putting in f of x, of course. Which is also, this is a degree n polynomial, and it has this form. Has the same sign at xj as fx minus Pnx. Why is that? Because we know that the deviation is less than ej, so this term is always going to be less than that term, and that means it'll have the same sign. But this implies that there are n plus 1 sign changes, and you should check that. And in particular, that implies that there are n plus 1 zeros, and you should check that. And n plus 1 zeros for a degree n polynomial implies, well, that this is 0, so these two polynomials must actually be equal to each other. Now, with these two polynomials equal to each other, this implies that the minimum j is less than or equal to dnf, which is our assumption, which is less than or equal to dfqn, which is strictly less than the minimum j. And that's a contradiction, so no such qn exists. Which gives us the result that we want. Okay, so that result can be used to prove something slightly more powerful, and this is by Chebyshev. A polynomial of degree at most n approximates f of x in polynomial of degree n, degree at most n, that approximates fx in our interval, is the best approximation if and only if f of x minus Pn of x assumes values so these are our EJs from before, except now we're assuming that the EJs are actually equal to the maximum deviation. And it has to swap sign backwards and forwards n plus 2 times. Right, any such polynomial is unique. Now I'm going to skip what turns out to be a rather important point in the proof, which is the existence of certain points, the selection of certain points. Of course, you need to be able to select a certain number of points, and those points that we're going to be selecting, the number of them is related to the number of times we change sign. So that's why there's an n plus 2 there. So first start, suppose Pn has the property and let x0, xn plus 1 be the points where maximum deviation occurs. As in the statement of the result. Then, based upon our previous notation, the absolute value of our EJ is the deviation. And so based upon our previous result, we know that dn of f has to be greater than or equal to dfpn, but that of course implies that, and this has to be greater than or equal to dnf by definition, so that implies that Pn is the best approximation. So now we need to prove the other direction. So we're going to start with this, and we're going to assume that it has the best approximation. We're going to assume that it is the best approximation, and we're going to show that it has this property, which is how we're going to do it. So in particular, we're going to assume that fnx minus pnx attains the values plus or minus dfpn with alternating signs at most k times for k in these values. Right, and we will show that this implies that we're not the best approximation. Right, now, so this is the selection of points. So we know that there exists xi1 up to xi k minus 1. So that we have x1, xi1, x2, xi2, xk minus 1, xk, and an epsilon greater than 0, so that f xi j minus pn xi j strictly less than df pn. And on intervals of the form a xi1, xi2, xi3. So these are intervals that end with an odd number. We have minus d f pn plus our epsilon is less than f of x minus pnx less than or equal to df pn. This can always be achieved because of the way we've selected the intervals and by the assumption that f is continuous. Essentially, the actual construction of the points is a bit painful, so I'm skipping that, and you might not like that very much. But you can always go look up this result in Isaacson and Keller. Okay, so we have a second type of interval to consider. And on intervals of the form xi1, xi2, xi3, xi4, so these are going to be even intervals because the index here is even. We have the result the other way around. Oh my goodness, no, this one is for even, and for odd we have I'm going to leave it to you to check that I have these the right way around now. I mean, I do, but I'm leaving it up to you. Draw a little graph, have a think about it. It's not super complicated, but you just need to understand what the function f is really doing, or what the function f minus pn is really doing at the xi's, and how it's traveling backwards and forwards and oscillating up and down, essentially. Okay, so take a new polynomial, rx. It's going to be the product x minus xi. So this is degree k minus 1, and has constant sign on each of the intervals, even or odd. I know I've only written down odd ones, but it does work for even too. I'll let m equal the maximum of the absolute value of rk. X goes from a to b. And I'm going to let q of x equal 1 minus k rx over 2m. And capital Q n x is going to equal p n x plus epsilon qx. So remember, this is degree k, so that's not changing the maximum degree of these things. Right. So it is possible to work out the following things. So we know that odd intervals implies if x is inside an odd interval, we know that our qx is built so this is true, and on even intervals we know that this is true. And so with these conditions it's possible to show that minus d f p n minus epsilon q x is less than or equal to f of x minus q n x less than or equal to d f pn minus epsilon 1 plus qx. And that's for odd intervals. And for even intervals, we have this the other way around. And both of those together imply that dfqn is less than dfpn, so that pn isn't our best approximation, but we assumed that it was, and so that's a contradiction, and so we know that it has to have the right oscillating properties. Now, why is it necessary to only have k minus 1 xi? Because if we had k xi, then we'd have k plus 1 changes in signs. Well, R would have k plus 1 roots, sorry, so it would be identically 0, because we want a degree k polynomial. We don't want to change the degree of Pn and Qn. There must be an issue with the signs involved. Have an investigate and a play and a think, because that's what it boils down to, the number of those ii's. It remains to show uniqueness, but that follows nicely from the number of changes in sign, just as we had before. So I suppose Pnx and Qnx are two best approximations. Then we can show that with some judicious application of the triangle inequality, that this is equal to dnf at n plus 2 points, because we've already proven that we have to have at least n plus 2 wiggles in order to be best approximation of degree n. Right. And this implies that at 2n plus points, that implies that qnx minus pnx vanishes at 2 plus n distinct points. And that implies that qnx is equal to pnx, just as it did in the previous result. And that gives us our theorem. So we know that these functions that wobble backwards and forwards, n plus 2 times, are the appropriate thing to give us the best interpolation. But what is the best approximation? Well, it's not known in general. But we can minimize the error, as I said. So minimizing the error is the same as we want this minimized. Which really knows we want the best degree n approximation to 0, because that's what we're trying to do. We're minimizing this, we're approximating 0, but it has to be a degree n polynomial. So this is a non-zero degree n polynomial, and that's the same as the best degree n n plus 1, because omega is n plus 1 degree, and that's the best degree n approximation to xn plus 1. We can construct these things explicitly, at least on this interval, and then we can make a transformation to construct them on other intervals. So if we have x inside here, then is at least well defined on 0 to pi, and I'm going to call this theta. So cos n plus 1 theta attains max slash min at theta j equal to j pi over n plus 1. J equals 0 up to n plus 1, and you should check this. Look, there's n plus 2 of those. They wobble backwards and forwards and they change sign. So this is a, well, it's not a polynomial. If it were a polynomial, it would be a maximizing thing. Well, according to the previous theorem. My claim is that this is actually a polynomial, so I'm going to define this thing to be some factor times cos n plus 1 theta, and that is going to be equal to some factor times cos n plus 1 cos inverse x. Okay, which has the required ordinating signs to be regarded as the best approximation according to this thing that we're looking for. How do you know this is a polynomial? Which is a good question. Just for the moment, I'm going to take little t n just to be equal to cos n cos inverse x, We note that t0 of x is 0, cos of 0, cos of 0 is 1. And we can say t1 of x, that's 1, the cos's cancel out, that's equal to x. There's a trig identity, n plus 1 theta plus cos n minus 1 theta equals 2 cos theta cos n theta. And that implies, and you should check this, tn plus 1x equals 2t1 x tn x minus tn minus 1 x. This is a polynomial in our functions tn's. We need two initial values to get this polynomial starting. We have two, and they're both polynomials, so this implies that. And in fact, you can claim more, because each time we times by t1, we get an extra factor of x, so degree n plus 1, in fact. And you should check, make sure everything I'm saying is true. Every time we increase the n, we get an extra factor of 2 out front, which implies that we should read it, because we don't have factors of 2 here. So we get tn plus 1 x is equal to 2 minus n, not n plus 1, cos n plus 1 cos inverse x, and this is equal to some monomial x plus 1 plus 2 times some other polynomial of lower degree. Those tn's are called Chebyshev polynomials. And xk equal to cos k pi over n plus 1, which is inside our interval that we're really considering. Tn plus 1 psi k is equal to 2n minus 1 to the k. So it oscillates backwards and forwards with deviation 2 minus n. So as n goes up, our deviation gets better, and we get a better approximation to 0. Great. And that implies that we should be able to take very nice interpolants with them. And the roots of the tn's should be the points where we're sampling our function, because of course we want this thing to be actually equal to the omega n. So take samples to be roots tn, and that implies that wnx as small as possible, which is great. If you want to do this in general, I've got my x over here, I have my y over here. Transform y of x is equal to 1/2 b minus a, x plus a plus b, and x of y, the inverse of this, pretty easy. The zeros, the roots, correspond to the roots that are pretty easy to find. And you check that those are the actual roots. Then the minimum deviation, or I should say the maximum deviation, and this should look like the Wn to you. If it doesn't, check that it is actually the absolute value of the Wn. Chebyshev polynomials minimize error. And a little lemma to drive this home. Let f be C2. Pn is the interpolating polynomial. Degree n, at most n, for f of x, based on our sample points being the actual roots, then pointwise is less than some constant regardless of, constant doesn't depend upon x, and of course that means that the Pn x will eventually approximate f. So the proof, basically it follows from everything we've done already. You can see this in 5.2.2 in Isaacson and Keller. So that is minimizing polynomials.